All right, let's talk about the secret rules that run the entire universe. I'm talking about the fundamental laws that govern literally everything that moves, from a simple rolling ball all the way to a massive rocket ship blasting into space. We're breaking down Newton's laws of motion.
So, here's what we're going to cover. First, the law of laziness. Then, we'll tackle the great F equals ma misconception. After that, the cosmic pushback. We'll meet the key players, the forces involved, and then we'll put it all together and see how the game is played.
Okay, let's dive right in. Our first rule is basically the universe's prime directive for being lazy. You probably know it as Newton's first law, or the law of inertia. To put it simply, things just like to keep doing whatever it is they're already doing. They are not going to start, they're not going to stop, they're not going to change direction unless something comes along and gives them a push or a pull. A book on a table. It'll sit there forever. A satellite out in deep space. It's just going to coast in a straight line forever, unless some force gets involved. Now, here's what's really interesting. Physics looks at both of these states, the object that's perfectly still and the one that's gliding along smoothly at a constant speed, and it calls them both equilibrium. Why? Because in both cases, all the forces acting on the object completely cancel each other out. They add up to zero. So whether it's sitting still or cruising perfectly, from a physics point of view, it's balanced. There's no net force acting on it.
All right, moving on to the second law. And I'm going to kick this off with something that might just completely change how you think about physics.
That's right. I'm telling you that the most famous equation in all of physics, well, it isn't really the whole story. It's an amazing, incredibly useful simplification for sure, but it's not what Newton originally wrote down. So, what is the real second law? The real key here, the crucial point, is that Newton's original law is all about momentum. And momentum is just an object's mass times its velocity. So force isn't just about making things speed up, it's about how quickly you can change their momentum. That's the real insight.
So, how do we get F equals ma? Well, it's this brilliant shortcut that works almost all the time in our day-to-day world. And that's because most things, like a car or a baseball, don't change their mass while they're moving. But think about a rocket. It's constantly burning fuel and getting lighter. For something like that, the original momentum equation is the only one that tells the full story. And now for the third and final rule of the game. For every single action, there is a reaction. You could call it the universe's ultimate rule of fairness. This means forces always come in pairs. Always. And here's the part that can kind of bend your mind. The pairs are always equal, and they're always opposite. If you push on a wall, that wall is pushing back on your hand with the exact same force. It's not a response, it happens at the exact same time. This is how rockets fly in the total vacuum of space. They push gas out the back, and the gas pushes the rocket forward. It's even how you walk. You push the floor backwards with your foot, and the floor pushes you forwards. Without that cosmic pushback, you'd just be slipping in place forever. Okay, so we've got our rules. Now let's meet the key players, the forces that we're going to see in our little game today. These are the ones doing all the pushing and pulling in our example. First up, we've got gravity, or to be more specific, weight. It's that constant, relentless downward pull from the Earth that keeps all of us grounded. It's always on, and it always pulls straight down. Our second player is tension. I want you to think of a rope as a chain of trillions of microscopic springs. When you pull on that rope, you're stretching all those tiny springs, and they all want to snap back to their original length. That internal snap back is what creates the pulling force we call tension, and it always pulls right along the line of the rope. So, we have the rules, and we have the players. Let's see how they all come together in a classic physics setup, a simple pulley system. This, my friends, is where the magic happens. So imagine this. You've got two weights, and they're connected by one rope that's draped over a pulley. Now, gravity is trying to pull both of them down to the ground, but at the same time, the tension in that rope is pulling both of them up. It's a classic tug of war. The heavier mass has a stronger pull from gravity, and that's what's going to drive the whole motion. And this setup just brilliantly shows you the core of how to use Newton's laws. You can boil this entire system down to one beautiful, simple idea. The acceleration of the whole thing is just the net force that's driving it forward minus what's resisting it, all divided by the total amount of stuff you have to move. Okay, let's break that down. The force of gravity on that heavier mass, that's our pulling force. It's the engine of the whole system.
But at the same time, the force of gravity on the lighter mass acts as a resisting force. It's being lifted against its will, and that's slowing the whole system down. And that is the real power of physics. It's not just a mess of random equations. It's a toolkit. It's a set of rules that lets us look at a really complex system, figure out the forces, and then predict its future with incredible accuracy. It literally turns chaos into order. And that brings us to one final big question to leave you with. Think about it. If you push on a box and that box pushes back on you with the exact same force, how do you ever win that tug of war? How does the box move at all? Well, that's a puzzle for another time. Thanks for joining me.